So I guess we can just jump into it. So our first question is, if you could have dinner with anyone, dead or alive, who would it be?
Maybe Ukrainian President Volodymyr Zelensky. Tell him to keep up the fight. That we're rooting for him.
Yeah, that would be a good one, especially because of I think he was named Person of the Year.
Oh,
So
was he?
yeah, that'd be very
Okay.
interesting.
Yeah.
I can ask the second question if you want, Bailey. I guess our second question was, can you tell us about your research in Greenland and researching snow and ice?
Sure. So people always thought that when pollutants were deposited in snow in a place like Greenland or really anywhere else, that the chemicals were preserved in the snow. And that's part of the reason why you can drill ice cores, right? So if you think about climate change, for example, one of the ways we know what carbon dioxide levels were in the past, one of the great ways to do that is to drill ice cores. So I mean, it's literally, you take a hollow drill that's roughly 4 inches in diameter, and you put it down into the snow and ice, and you keep pulling up the tubes of ice. And then you can go in there and analyze the levels of carbon dioxide in the air bubbles. So that's a great example of how ice cores are used to understand what the atmosphere was in the past. And the assumption has always been that whatever gets deposited is just preserved. But about 20 years ago, some scientists working in Greenland found that there were lots of nitrogen oxides released from the snow. I don't know, have you guys talked about NOx?
No.
Okay,
I don't think
yes. So NOx is a major pollutant that's responsible for making ozone, which is part of smog. So this was surprising to people that in this pretty remote, very clean Greenland that you're getting this NOx emission from the snow. And what they found was that nitrate, NO3 minus, which is another ubiquitous pollutant in the atmosphere, was being broken apart by sunlight in the snow and making NOx. That's a gas, and so it would go to the atmosphere. So that got lots of us interested in what kinds of reactions might the sunlight be initiating in snow. So we went to Greenland 3 times to look at a couple different questions. We were interested in how deep does the light penetrate into the snow? And it turns out that it can get several feet into the snow. So all of that region could be undergoing chemical reactions from sun. We were also interested in the formation of radicals in the snow. So have you guys done chemistry in your atmospheric science class?
We reference parts of what we've learned in chemistry, but
Okay.
not a lot.
So a lot of the chemistry in the environment is driven by radicals. And one of the most important ones is called hydroxyl radical. And so we measured the formation of hydroxyl radical in the snow and how quickly was it formed and how much was there and what might the implications be. So we were interested in snow mostly from what's called a photochemistry perspective, how light initiates chemical reactions.
That's awesome. I actually never heard, you said it was an ice core. What was that called again?
Yeah, it's called an ice core.
Ice core. I've never heard of that being used to track certain things before. That's so interesting. The only thing I've heard of it is with ice fishing, which is so funny.
Oh, yeah. Well, in Greenland, the top of Greenland, it's a place called Summit, and it's really just a research camp. If there weren't scientists and the support staff up there, there wouldn't be anybody living there because it's all just snow and ice. There are no trees, there are no rocks, there are no animals or birds, but the ice layer there is about 2 miles thick.
Oh, wow.
And so it's over 100,000 years old at the bottom. So that's why the ice core works, is because you've got these layers of snow that build up and build up and build up. And then you can go in there with this drill and go back in time, essentially 100,000 years. They're currently planning an ice core in the Antarctic that they hope can go back 1 million years.
Oh my gosh.
So that would be a great record of how the atmosphere and how climate has changed.
Are the
Yeah.
ice core, oh, sorry.
No, go ahead.
I was going to ask, are the ice cores affected by climate change in any way?
Yeah, definitely. And the ice, I mean, problematically, ice is melting, right? All around our world, including in the Arctic and the Antarctic and continental glaciers. So that's a issue. But these cores are great records of environmental change, including climate change. It's incredible what they can get out of these ice cores. You can measure the gases in the bubbles that are trapped, from 500,000 years ago. But you can also measure what's called the isotopic composition of water. Have you guys had chemistry?
That sounds familiar.
Yeah,
Yes.
Yeah.
I think
So
2 years ago.
okay. So if you remember the idea of an isotope, it's so two things are isotopes if they're the same element, but they have a different number of neutrons. So for example, hydrogen and deuterium, they both have one proton, but deuterium also has a neutron and hydrogen doesn't. So they're isotopes. So chemically they behave very similarly, but they have different molecular weights because the neutron has a little bit of mass. So you can look at the isotopic signature of the water in the snow, and that'll tell you what the temperature of the earth was when that snow was formed. And so you can determine temperature records from ice cores, and that's one of the major ways in which they're used. So if you look at temperature records of the past, let's see, the oldest ice core we have right now is about 600,000 years old. So the best temperature record of the past 600,000 years is from an ice cores. So it's great. You can get chemical information, you can get temperature information, you can get a whole bunch of other information too. So you can see what the Earth was like through quite a bit of its history.
That's really interesting. Our next questions, it's a little more vague, but it's what does your research usually entail?
Yeah, so most of my work is done in the lab. And we did a bunch of work in Greenland, as I mentioned. But other than that, I generally work in the lab. We sometimes collect samples in the environment. We're doing a lot of work on particles now. So particles are solid or liquid material in the atmosphere. They're very small. They're between roughly a nanometer and 10 micrometers in size. So for comparison, like a hair is about 50 micrometers in diameter. So they're too small to see, but these particles are really important because they impact climate, and they're also toxic to humans. So there's a lot of interest in what are the sources of particles to the atmosphere and how can we reduce the emissions of particles and of gases that make particles. So the work we do, we've got some work on snow, but we've got more work actually on particles. And we're trying to understand the chemistry in particles. And again, mostly driven by light. So what happens when sunlight shines on these particles? And what reactive species do you form? And how do they either make the particles grow or make the particles shrink? That's the kind of the bottom line.
Can I ask which one do you like more between the two that you researched?
Yeah, good question. I did snow for about 20 years. So I'm more interested in the particles now because that's a little newer. Yeah, and it's a little more relevant. I live in California, and where I am, we don't get a lot of snow. So, but we always have a lot of particles. So it's a little more relevant to humans.
That makes sense. Did you make a lot of the switch from snow to particles? Oh, my bad. Over COVID because you were unable to travel, or was it just an interest switch?
No, I've been studying particles for maybe over a decade. So, yeah, when I first started at Davis, which was 26 years ago, I did a lot of research on fog. So looking at the chemical reactions that happen in clouds and fogs. And then I switched from that after maybe 6 or 7 years because Davis used to have a lot of fog in the winter, and then it started to disappear. And people aren't 100% sure why it's been disappearing, but our winters now are much less foggy than they used to be. So I made the switch at that point from fog into particles, because there are a lot of similarities actually chemically between the two, but particles are always around and fog is only sometimes around.
That's so interesting. I'd never heard of like a fog just all of a sudden disappearing. That's crazy. So the next question is, do you enjoy the balance between teaching and doing research? And what made you switch to being a professor?
I do like the balance between teaching and research. It's nice to do both. They're very different. Research actually involves a lot of teaching as well, but it's for graduate students. So I have roughly 6 people who work for me, and they are doing experiments in my lab mostly. And then I'll meet with each person every week for half an hour, and they'll tell me what they did and what they found. And then we'll talk about the results and try to understand what's the best next step. And, how do we interpret what they found, and what does that mean about what we should try for the next set of experiments? So that's also teaching through the research, but it's not classroom teaching. But classroom teaching is fun too. It's nice to spend time with students. Students generally have a lot of energy, at least until the end of the quarter. Then everybody's tired. I'm sure you guys appreciate that. But it's nice being able to, be around that energy with students, and hopefully give students tools that they can go out and make the world a better place. So I like both research and teaching. They're very different and they're pretty complementary.
I had never thought of like the research aspect of being a professor to be like also in a teaching position just with older students. That's
Yeah.
very interesting.
And then the question, what pushed you to switch to being a professor?
Yes.
So from what?
I know you mentioned you were teaching at a boarding school before.
Oh, I see. Right. Gotcha.
Yes. I was just interested what made you want to switch.
Yeah. So when I finished my undergrad, I was a chemistry undergrad, and I knew I wanted to go back to grad school, but I was tired by the end of my undergrad time. So I needed a break. So I took 3 years off. I taught 2 years at Miss Porter's school, high school chemistry and physics. And then I worked for a year in an analytical lab. And then I went to grad school. And then after grad school, I did what's called a postdoc. So it's a period of a couple years, typically, where you try to broaden your research experience. So that's for my grad school time. I researched cloud chemistry. We were looking at acid rain chemistry and how acid is formed. And then I wanted to get experience with particles. So I did a postdoc in Canada on particles. And I knew when I was doing my postdoc that I wanted to be a professor. So yeah, after my postdoc, I came to Davis and was being a professor. High school was great. I enjoyed it, but boy, it's very repetitious.
Yeah, I can imagine.
So
Every year.
yeah, the same, right? Freshman chemistry or general chemistry is very similar year to year. At the university level, you can make things a little more different.
Do you find that there are lots of overlaps with chemistry and atmospheric science?
For what I do, yes. Atmospheric science is a very big field, and you got people who do like very meteorology focused, trying to understand, wind patterns and how things move around. And then I'm on kind of the other end, which is the chemistry. So I couldn't tell you how winds move around. I can't look at a weather map and predict what the weather is going to be like in a couple of days. But I can tell you about chemical reactions in the atmosphere and how they influence human health and how it affects climate change. So atmospheric science is a nice field because there's a lot of variety, and you can do actually pretty different things within atmospheric science.
Yeah, I think also after just the few months that we've been studying this course, we've seen how many things there are to cover in one topic of science.
Yeah.
Awesome. I'll ask the next question. So what do you want to ultimately achieve with your research?
Yeah, we try to understand how the atmosphere works, chemically, how things happen, if, for example, in particles. And we're very interested in what the implications of that are. So, for example, our particle work, there's a lot of focus on how do you make new particles in the atmosphere. Again, particles are toxic, and so the more particles there are, the more dangerous they are to humans. So we're very interested. We've been looking for a number of years now at how, if this is a particle and you've got gases, floating around outside, when light shines on the particle, you make these oxidants, and then what happens is the gases are always colliding with the particles. And when you have the oxidants made in the particle, when the gas collides, it can react and then make a species, make a molecule that's bigger, and then it doesn't go back to the gas phase. It stays in the particle, and then the particle can grow and grow. And so that's going to lead to more health impacts. So I'm interested in trying to understand how chemistry in the atmosphere increases or decreases particle loading, so that hopefully regulators can understand how to reduce the particle concentrations in the atmosphere.
Right.
Is that is the particle concentrations, are those geographically specific? Like, would they be different in California versus New York City?
Yeah, definitely. And it's even different from day to day.
Oh, okay.
There must be days in New York City when it's kind of hazy. And it's a little grayish or maybe a little brownish. Those are particles scattering light. You can't see the individual particles, but you can see the impact of particles on visibility. And then other days it's beautifully clear, right? Perfect blue sky, you can see really far. That means you have very few particles in the atmosphere. So it definitely changes from place to place, but also for a given place, it'll change from day to day. In the West Coast now, we've been having, for the last several years, really bad wildfires in the summer. And that's now a major source of particles for us, which is bad because people really need to stay indoors when you've got these really bad wildfires and the particle levels are really high. People should stay indoors so they're not getting exposed to all this air pollution.
Right.
And I guess our last question is, why did you choose a career in atmospheric science?
Yeah, I wanted to help the world. And I also wanted interesting puzzles. Like, I like to solve problems and puzzles. That's one of the great things about science. You get to be a detective, essentially. There's a question you're trying to answer, and you got to look at all the evidence, and you try to make your own evidence, and then you get to, hopefully at the end, come up with the answer to the problem. So I like to do that, but I don't want to just solve problems. I want to solve problems that make a difference and hopefully have an impact on the world and make things better for people.
That's really inspiring, very sweet.
I agree. That's a fantastic goal. And I know that just thank you for sharing with us. I mean, I know that our interview would be very helpful in our project, and I'll keep you updated too on where this project takes us. And yeah, just thank you so much.
Yeah, you're welcome. It was a pleasure to meet you all, and best of luck with your project. And I'll send you the link once I get it. It usually takes
Thank you so much.
An hour or two.
Okay,
Yeah.
thank you.
All right,
Thank
have
you
a great day.
Have a good day.
Bye.
Bye.